In this video I will do experiments on frequency doublers, mostly active ones. And here is the setup. I have a local oscillator on 10 MHz at 1 watt output power, and then a stepped attenuator with up to 30 decibels of attenuation. And then device under test, that's a frequency doubler. Then there is a 20 dB coupler into which I can send a signal from a signal generator. The other side of the coupler has an impedance match and a resistor, so I can tune this to send no signal backwards into the device under test. Means since the output impedance here could be something different from 50 ohms, I don't have the error of sending something back that would then be reflected this way. So I know I'm sending a signal only like that. And then this second coupler will take out whatever goes through here. And that is the signal at 20 MHz produced by the device under test and the signal injected here. And then this coupler takes out about minus 20 dB, and I look at that with the net aphery. The output here, the main signal, goes to a selective load that presents a 50 ohm impedance on 20 MHz. And then there is a quarter wave cable that will change the impedance of this, a quarter wave cable, and then there is a notch at 20 MHz. This quarter wave cable makes the zero input impedance of this notch to be a very high impedance at this point. Means that the 20 MHz signal will see only the selective load, which is 50 ohms. And then the notch is followed by a quarter wave cable and another notch. And the cable mirrors the impedance, so the low impedance out from here becomes a high impedance here, which makes this notch effective and causes the impedance to go very low. And then another quarter wave and another notch, another quarter wave and another notch. That is to suppress 20 MHz efficiently all the time, without the need of careful retuning. Then there is a bandpass filter on 20 MHz, because the frequency multiplier up here, it may generate other overtones than 20 MHz. And since I want to look at the noise floor, which is very low, I have to apply a lot of gain, and the overtones at maybe 30 or 40 MHz, or even the fundamental at 10 MHz, or even higher frequencies, multiples of 10 MHz, can saturate these low noise amplifiers. And if they don't, they could saturate the SDR IP. So this is a very important thing, to have a good bandpass filter here with low insertion loss and good rejection at other multiples of 10 MHz than 20 MHz. And finally, the SDR IP to analyze what we see. This is the first circuit that I'm testing. It is two N4427 bipolar transistors in push-push. No bias, nothing. It's just this transformer to transform the signal to a push-pull signal. And then the two transistors, I go into the emitters through 47 ohm resistors. Collectors in parallel, and then an output transformer reducing the impedance slightly to get the maximum output I can get from this. And here is what it looks like. A very simple thing and primitive design. Just for testing how does this thing work. Here is the netafedri, and I calibrated the carrier at 20 megahertz here to show on the S-meter 0. And then I switch on this in extra signal at 19.9. That's 100 kilohertz below. And it comes, of course, at 19.9. And I click on it and center it into the filter. And then look at the level. Oops. 79.9. So I need 0.1 decibel more. Sorry, 0.1 decibel less. So now it shows minus 80 decibels. And I switch for the SDR IP here. And I'm looking at the signal at 19.9 here. And I want it to show minus 80 decibels. Minus 79.95. That is close enough. 79.98. Well, so I switch off this. And here comes the noise floor at 100 kilohertz separation. And the bandwidth is 1 kilohertz. And I read it out. Minus 133.4 means minus 163.4 dBc per hertz. Here is the sideband noise from measurements I made in the previous video on Schottky diode frequency doublers. And what I found now is here. It's about 15 decibels worse than the Schottky diode frequency doubler when run at maximum power. So this is not promising at all, at the first glance at least. Now this spectrum looks pretty odd. There is here some fairly sharp structure, and on the other side the same, but the symmetry is different. It goes up and then down, and here it goes down and then up. I shift the frequency by half a megahertz, like that. And then you can see the noise goes up 5 decibels or 7 maybe. And the whole thing looks odd. So I will do some interesting experiment. This is a strong magnet, and I put it under the box like that. And then look here while I move this magnet. Look at the spectrum. How the sharp structure disappears. How this peak moves in frequency. And how the general level, now the magnet is close. And now it is far away. Now of course I'm changing the inductance of the transformer, so I will look at the netafedri to verify that I don't change the level of the signal, means the 20 megahertz signal, which is here, and it should be at 0. And I move the magnet close. Now it is at the closest position. I have lost maybe 0.5 dB or so. The the loss of signal level is very small. So that doesn't explain what I see. It's not a matter of saturating the core so there is no signal through it anymore. So I go back to the spectrum here, and in order to get rid of those sharp phenomena here, I can hold the magnet in a fairly large separation. And you can see the feature shifts in frequency also. Now there is one more core, so I use the magnet on the input core here. You can see how it moves when it is attracted by the magnet. So here is what I have with the magnet on the input core, and I remove it, and it makes a very big difference on the noise. Something like 2.5 division means 12, 13 dB or so. And I look at the netafedri, and you can see the level goes down by maybe 3 dB. So it's not that only that the level goes down. There is something magic on the ferrite cores. And I think the noise I see has to do with magnetostriction in the iron. Means that there are mechanical vibrations in the iron at very high frequencies caused by magnetostriction. And how they couple and how they make these resonances at some offset of the signal, I don't know, parametric oscillations of some kind, coupled through magnetostriction. So I will try to change this design by making these cores, these coils, transformers, iron-free. I have modified the output like this. An iron-free coil and 2 tuning capacitors. So I can get impedance matching by selecting these two appropriately. And this is what it looks now. And I still have the ferrite on the input side. The sideband noise is very strong now, and it happens to be at 100 kilohertz offset. And there is a second peak at about 800 kilohertz. So I take this magnet again and approach the transformer from below. And it's clear that the sideband noise changes dramatically. I remove it again. So the position of this peak and the level are very strongly affected by this. I look in the ephedry for the signal level. I have lost 5 decibels of the 20 megahertz, but the noise has gone down by 20, 40, 45 decibels. So this is a very much nonlinear effect. So now I remove that magnet and reduce the input power instead. This is 3 decibels less power, and the improvement is something like from what's here, 143 and 121. It's 22 decibels or so. But the signal level has gone down by 3 decibels only. So what happens is very sensitive to the input power. I put the magnet there now again. And of course, noise goes down. But the signal also goes down quite dramatically. So I remove that magnet again and go back here, and now I increase the voltage. It's now 14 volts. And now it's about 25 volts. And I'm not sure the transistors are rated for much more than this, but you can see more voltage means a better performance. So the whole thing is a little bit peculiar, I think. So I will replace that input with something iron-free and look what happens then. I have now changed the input like this. So it's a trifilar winding on an air bobbin. 7 turns. And it looks like this. And I had to place about 300 PF or maybe 250 in parallel with the input, because the inductance was a little bit too low on this coil. But what I see now is more or less exactly the same as I saw with the ferrite cores. So the problem is not with ferrites at this level, and I have these two peaks, one close spaced and one wide spaced. Now I take this electrolytic capacitor, 1000 micro, and connect it on the supply voltage like this. And it's clear that this close range peak comes from AC on the supply voltage. But the wide range noise peak does not change at all. You can see the mouse cross, and I remove that capacitor and things look very much the same. So I will start now by filtering the supply voltage properly and see what remains. 10,000 microfarads and 10 ohms will remove noise from the supply voltage down to very low frequencies, because maybe I will look at close range noise a little bit later. This fixes the close range problem. There are some little structures here that I will look at later, because first I have this problem with a very strong noise hump at the separation of about 350 kilohertz. To understand the problem with this hump, I insert a 3 dB attenuator, this one, after the frequency doubler here. Well, first I have nothing connected, and then the noise has gone up. Well, I have the pilot tone there. I remove that. Here is the noise floor, and it's pretty low. And then I connect the frequency doubler through the 3 dB attenuator. And here is the noise floor. And I also look at the noise floor at the hump here. And then I disconnect the attenuator and connect directly. And we can see that the noise has increased by far more than 3 decibels. It's from here to here. That's 10 decibels. While at the close range here, I don't remember exactly where I was before, but it was this level, and now it is here. And that is a much smaller change. I will insert the attenuator again. And it's clear at this point the noise is reduced by, I clear the screen so I can see better, from here 142 to here 144. That's only 2 decibels. So this attenuator does not change the noise floor by 3 dB. It makes much bigger changes, and the reason is the impedance is not 50 ohms. And the amplifier I'm using is very sensitive to the impedance. It's an PSA 4 minus 5043. It's an MMIC in gallium arsenide intended to operate above 50 megahertz. So it has a very high SWR at this frequency. So this is obviously not a good configuration. I will change that amplifier. So I disconnected this PSA 4 5043 and instead connected this QBH 1297. It is a little bit more noisy, but it is 50 ohms because it has a 50 ohm 50 ohm attenuator before the next LNA. And now the noise floor looks reasonably flat. Of course, the source impedance is still varying a lot, but that doesn't affect this 50 ohm amplifier by far as much. I have tried to improve the performance of this frequency doubler by adding a bias on the base and by changing this source resistors. This has not given any advantage. I have here on the input an impedance match box that I have to retune when changing things. And of course I have also to retune these output capacitors. But nothing makes a significant improvement. The signal level in the ear is set to 0 on this S-meter scale. And then the signal at 19.9, that's from this signal generator. It's now at the center of the frequency, and I read it as minus 79.96, or once more, well, minus 79.96, that's 0.04 dB error. I don't care about that. Then I look in the Linrad spectrum for this signal at 19.9, and the level I see is minus 79.998, so it's minus 80. And I switch off this signal generator, and here is the noise floor at the bandwidth of 1 kilohertz. And what I see is minus 144.6, means minus 174.6 dBc per hertz. The injected signal is now 5 kilohertz below the carrier, and I have set the calibration for it to show minus 79.999, means minus 80. And then I look at the spectrum in Linrad, and it has to be 5 kilohertz below, it's here, and things have changed a little, so I need to change calibration a little. The meter now shows -80, so I switch this signal generator off and look for the noise floor. And it comes here. Well, this camera gets reflections of various kinds. Here it is, and I read it out. -144.8 means -174.8 dBc per hertz at 5 kilohertz. As compared to the Schottky diode mixer used as a frequency doubler, it's this curve at a high input level. Here the active mixer with these bipolar transistors is the same, and at 5 kilohertz it looks a little bit better. And I cannot measure at close range with a single unit. I would have to make two of them and look at them in the interferometer. But I'm interested in having a lower level at wide separations. So this design is not an interesting candidate to make further studies. Here is the spectrum. The 20 megahertz signal is at plus 25.3 dBm, and the input at 10 megahertz is plus 30 dBm. So conversion gain is minus 5 dB approximately. I now put 3 BC338 transistors in parallel for each of the transistors. I need 3 of them to absorb the power because I want to run at 1 watt input. The carrier in the ephedry is very close to 0, and the reference signal 100 kilohertz down, it's here. I have to click it into the filter, and then I can read the level. -80. So I have to set Linrad to show -80 on this same signal. And you can see here it actually does. So I switch off that generator. And here is the noise floor, 100 kilohertz away with 3 times BC338 for the 2 transistors in the frequency doubler. And I see -146.98, that is -147, means -177 dBc per hertz, because I still have 1 kilohertz bandwidth. That's here, marginally better, not really interesting. This is 4 times MPSH 10 in parallel on each side. This is a UHF low noise transistor. I had to put the resistor here between gate and ground to avoid UHF oscillations on both places. With proper calibration, the noise floor is at -148 dBm or dBc per hertz in 1 kilohertz, means 178 dBc per hertz. That is marginally better than I saw with BC J337 is here. So I haven't any solution to the problem. I want the noise floor to go down significantly below what I have seen with bipolars. This is 4 times J310 in parallel on each side. It's an N-channel RF amplifier transistor, a JFET. I verify calibration. This is the carrier here with the ephedry, and then I have this reference signal which happen to come within the filter like that, and the level here is minus 80.0. And then I look in Linrad. I have this calibration signal in the passband center, and I have set to show 80.07. It should be 80.0, like this, and then I switch off that calibration signal to see where is the noise floor now with 4 J310 in each leg of this push-push multiplier by 2. It's minus 152.5 in 1 kilohertz, means minus 182.5 dBc per hertz. So that is here, significantly better than I have seen with the bipolar transistors. I made some changes. Firstly, I increased it to 8 transistors in parallel in each leg, and they are now J310. I increased the number of turns on this bobbin to make this capacitor a little bit smaller. This didn't make any significant difference. Then I removed the resistors from being one here and one here to put a common resistor from this point to ground. 47 ohms still seems to be an optimum. But then I added a series resonator here that is tuned to 20 megahertz. This increases the power output by almost 6 decibels. Because the current that I want to flow here has to flow this way also. And this resistor would provide feedback and reduce the power on 20 megahertz. So I just short it like this. Putting a capacitor to ground here gives various complications and higher noise. I don't know exactly why, but it allows a lot of current on other overtones to flow. So that's probably the reason. And here is what it looks like now. Output of the transistors, 47 ohms. The tuned circuit for 20 megahertz on the sources. And the input, and this is the bobbin. So I put the lid back on and look at the performance. So I calibrate the usual way. 0 for the carrier, and then for this reference signal, 2 kilohertz below 100 kilohertz, because there is a little spur here. The level, is minus 80. So I go over to Linrad to look at the noise. And here is a problem. You can see close to the carrier I have these bursts of noise coming up and down. These are from the crystals. The crystal notch filter is not happy with this power level. So the result I will get could be a little bit inaccurate. And I have to calibrate the level of this injected signal first. Like this. And then I switch off this pilot tone. And here comes the noise floor, which could be a little bit unreliable because of noise in the crystals, but if there is some error, the noise has to be better than what I read here. And what I see is minus 159.93. That's minus 159.9. Well, once more. 159.9. That gives a point down here. Minus 190. The 10 megahertz oscillator at 100 kilohertz is minus 197 or maybe minus 195 or so. I don't remember which one is which. Now, multiplying the frequency by a factor of 2 should increase phase noise by 6 decibels. And this point happens to be 6 decibels up. But it's only the phase noise that is multiplied, and the phase noise is 50% of the noise. So this frequency doubler is not perfectly ideal, but it comes reasonably near. To look at close range, I inserted a 10 dB attenuator on the output side. That reduced the signal by almost 10 dB, as you can see here. So I have to recalibrate like this. The signal is now 5 kilohertz below the carrier, and it comes at minus 70.2 for the 10 dB attenuator. So with a small adjustment, it comes at minus 70.0. And now I placed that signal at minus 69.98, very close to 70, and then switched the generator off. And here comes the noise floor at 5 kilohertz offset and in the bandwidth of 1 kilohertz. Minus 149.3 means minus 179.3 dBc per hertz. This comes here, and it seems to be flicker noise, judging from the slope between these 2 points. But that's not the case, because then I should expect to see something lower here, which I don't. So we have to consider also the 10 megahertz signal. At 5 kilohertz, the noise has started to go up by almost 10 dB as compared to 100 kilohertz. So if I do some speculating about it like this, at 10 megahertz, 5 kilohertz offset, I see minus 185 dBc per hertz, and that is the sum of the noise from 2 oscillators. So the phase noise of 1 should be the same as the amplitude noise of the same, and they should be at minus 191 dBc per hertz. Now, that assumes that the oscillators are identical, which they are not quite. At 20 megahertz, due to frequency doubling, the phase noise has to increase by 6 dB to become minus 185 dBc per hertz. And what I observe is minus 179. So the multiplier degrades by 6 dB. maybe it adds amplitude and phase noise equally amounts at minus 182 dBc per hertz. And I need to do some work with the soldering iron to get a better idea about this. Here is the power spectrum on 20 megahertz. Well, from DC to 100 megahertz. And the 20 megahertz signal is 27.5 dBm. And the input power is about 30 dBm, so the conversion gain is minus 2.5 dB approximately.